the morning, or for this session, by Frank Reitz, and it is a new convection scenario in granulates under geometrical restriction.
If I take the discussion last evening serious, I have to excuse myself first, as my experimental work doesn't contribute anything to the unification of the granular theory. Opposite. Rather, it increases the uncertainty. It adds more segregation and more convection and more disorder. And my work deals with the transition of two systems that they are between a densely packed system and a loosely packed system and a densely packed system. And you can find very strange things. And the work is done in the nonlinear group Magdeburg. It's near to Berlin. And my supervisor is Professor Ralf Sternaris. So as it is important for my work, I first have to introduce or repeat the agitation of granular matter, their rotation and vibration. And there we have the classical drum invented by Oyama 70 years ago. It was a Japanese engineer. And this experiment we also investigate in Magdeburg. It's done by my colleague Thilo Finger. And this drum is filled 50% with mixture. And after a few rotations, we find this radial segregation. And on a longer time scale, we can see this axial segregation. So you see this here in a movie. These processes are very slowly, so you have to speed it up very extremely. So you can construct a time-space plot. And I think most people know this, and Kimberly Hill, she also did many experiments some years ago. So on the other hand, you have vibrated systems. They are highly fluidized, and you can find convection rolls, or you also find segregation. But segregation is characterized by just a simple top-down structure. Sometimes you also have a sandwich structure, but it's not very complicated, the segregation. So, as you see here, you have to agitate very strong, 33 times the gravitation, and you need a minimum gravitation of 1.2 the gravity. So, my setup consists of a flat container, this side view cross section, and it's half a meter long. And the most important fact is that the cell is very thin, so you can call it a Hay-Shaw cell. And the cell is filled with a granular mixture, almost completely filled. There's only a small gap here. This is the small gap of air. And the cell is rotated along the horizontal axis slowly so that the inertial forces are negligible. And one positive effect of this container is that we can look through from this direction, because only 0.5 millimeter, that means only 5 to 15 beats. So this is the setup. Here's the cell. And rotation axis. Here you can see how we take pictures. The cell is rotated, then stopped, then some pictures are taken. Then again it's rotated and picture is taken. So we have to stop the container, but it doesn't influence anything. So if we combine these pictures, we can create a movie. You will see later. So the decisive parameter of my experiment is the fill ratio, and the fill ratio shouldn't be mistaken with the packing fraction. We define the fill ratio by the ratio of the net volume of glass beads and the container volume. So we take into account the whole container volume, And the net volume we can calculate by the mass and the density of the beads. And if we completely fill the cell, then we get a value of 0.66. And we can tap it also, then it increases. But you should just remember this value. And we find the critical packing for a value of 0.6. It means it's on the upper limit. And for a packing fill ratio less than this value, we find this axial segregation bendings. This I call a shoot flow regime. And if we increase a little bit the packing, the fill ratio, then we find convection rolls. And it's completely different regime, and I will show now in detail. This is a time lapse of the
If you put it so it just displays on the projector.
Yes, I tried.
Yeah.
But that's now very slow. This is the most important what you have to see. What's this? Maybe technician can help me. So.
You've got it just displaying.
Should I change the resolution?
Sorry?
Should I change the resolution? Or?
No, can we get the video working just now? Like this?
Or can you, put it on the screen and then let's see if I can get it looking on the screen.
What slide do you want to show?
No, I don't know the number. It's here, so there must be a movie, but I have to start the presentation. Start in the presentation mode. And if I press F5, then I get.
I can change that.
Yes.
Right, okay, let's change that.
And the height. Oh. Okay, now I should. Okay. Again, now we are in the axial segregation regime. It means the fill ratio is lower than the critical value, so we get this axial segregation as in the rotating drum, and the bright stripes are the large beads. So, and the whole packing is fluidized. So, this is the direction of rotation, and what you expect is that also the granulate flows in the same direction. So, now we increase the packing fraction, and you see the dynamics is slower. and you get these very regular shaped rows. It's similar like in the Rayleigh-Bénard system. But you can see by naked eye you have to sped it up. And you also see on top and bottom layer, it's high fluctuation, so this is the only place where the fluidization takes place. And in the center, there's the granulate is jammed. So yeah, you have two principal different areas. So let's again look it faster. And these rows are long-term stable, so you can rotate some days more, and sometimes they change it in the number of rows, but they also can stay stable. So to quantify, I use cost correlation. It's the same like PIV, and you can see here it easily can detect the motion, and I can calculate the flow field. And you see these flows are in the same direction and the opposite of the rotation direction. So for further investigation, only the vertical speed in the center is of interest. And you can here see it very good, and speed range is about 10% of the small diameter. And then you make a Fourier analysis and you get the mode. The main mode is the CR5, and it fits very well. Mode 5 means that you have 10 rows, so it's always a double. So now we change to a color system, and blue means downwards, like water, and red upwards, like fire. And only it's of interest the speed in the center. So we can construct time-space plots from top to down, and you can see here the evolution of these rows. And this is also a difference. For example, you have upwards motion at the right side and downwards motion in the left side. So this is different from vibrated systems. In vibrated systems, you always have the same motion, same direction on the edges. Now we can look how the transition takes place, and the transition to the convection regime. And this is a time-space plot for fill ratio less than the critical value. And you see here with this scale, everything moves down in the direction of rotation. And if we increase the fill ratio from left to right, you can see that step by step these rows develop. And if you approach the maximum value of 0.66, then the amplitude of speed decreases. Because if you fill more and more in the container, then at one point nothing can move because there's no space. And for this experiment, for example, there's only 2% free space on top of the granulate. The rest is occupied. So now let's look how the geometry influence the rows. First, we change the container width and height. So here we have the number of rows as a function of the container height, and points means that the number of rows was constant in the experiment. And this stripe means that the row number fluctuated during experiment. And the red curve indicates what you would expect if you assume the roll is circular, and you can see that that fairly this condition is fulfilled. So now we change the width. It's a container only 8 centimeter width, and here you see that that you have a single roll, and if you look carefully, you can see that the speed is oscillating. It's a period of about 2 hours. So we also can decrease the size of the container. Here we have a small container of only 4 centimeter by 16 centimeter, and you see that the rolls are very conspicuous and they are more regular than in this big container. It looks like a pocket camera, this pattern. And here you see a computer tomography exposure, and you can identify each large particle. The small particles are not detectable. And this example shows that the transmission technique is reliable.
Could you tell us sort of how big your particles are?
The larger ones are 850 plus minus 50 microns, and the smaller 350 plus minus 50. So in this container we have about 500,000 particles. So, and I want to decrease the dimension more and more, and identify the smallest possible size. That is important for simulations. So now I change the profile. So, and from left to right, the thickness increases. Here we have a very thin cell, only 0.3 centimeters, and we can find convection or axial segregation. The reason is that this cell is too thin and the granular, the beads clocking. And for this regime, you find convection and segregation, axial segregation, until a thickness of about 1 centimeter. But if you increase the container thickness more, then I couldn't find convection. So, but there's also another problem that I now approach the limit of the transmission technique. So, because I can't look through 2 centimeters, there are too many particles in the container. But there is one paper. It was published 2 years ago, and they rotate a drum and with high fill level, 90%, and then after 2 hours they cut this container after they freezed the particles. Oops. And this is the slice along the horizontal axis, and you can see that inside the drum there are some strange structures, and they think that it must be convective currents, but they can't observe because they always have to destroy the drum. So, but maybe this is related to my work, and there's no other literature comparable to my work. So now we can force the positions of the rolls with a modulation of the container height. So we have here a modulation of 1 millimeter, and here's more space than here, and you can see that always the motion is upwards at these positions. And this can maybe a clue for the mechanism of the convection. Then I think that maybe there is a natural modulation of the granulate, but this I have to check later. So now we go back to the shoot flow regime. It means the fill ratio is less than 0.6, and here we have seen already this is the time space split for the drum, and this is the space plot in my system. So, and at the beginning, it looks the same, but something strange happens after 4 days of rotation. So the contrast is a little bit weak. So, but you can see that they are traveling waves, and the time-space plot looks like this. So, but this I also have no explanation, and this should be investigated in another project. And this experiment took place about 2 weeks, and waves didn't stop, so but they couldn't wait longer. So this is my summary. I found a new convection mechanism at high fill fractions, and the most interesting fact is that I have a transition from shoot flow to regular convection rolls. And the origin of convection is not understand. Maybe you have a theory. And it can maybe be interesting for systems where fluidization is restricted, maybe in soils, where you can find these stone rings. So,
Where is that picture from?
this is from Nature paper, Kessler.
Yeah, about the location.
Oh, this is a desert in the United States, I think.
Is it ice? Is it ice?
No, it's a region where you have a lot of freeze-thaw cycles, daily cycles. Freeze-thaw, because you need a lot of cycles.
Isn't it a permafrost and that the
Yes.
melting over the permafrost?
But the permafrost thaws every day.
But there is an explanation for this. This can be
Yes, but
interpreted in terms of a planar convection with phase changes between ice and water. I've forgotten the literature, but I could dig it out.
so thanks for your.
So do we have further questions or comments?
Sorry, it's on classical hydrodynamics, the Bénard and Bénard-Marangoni instability. Again, you have got convection, and you've got different type of convection pattern in that would be in 3 dimension. Whether you have got a top glass plate, or whether you have 3 glass plates. I mean, one of the things gives you, if you've got a top glass plate, gives you rolls, which are similar to the one which you have here. And then you have got cellular type of pattern when you have got a free glass plate. Now, it seems that in your case, your granular material, apart from the roll, you have got a fluidized, you said you have got a fluidized layer at the bottom. I mean, the machinery implies a fluidized layer at the bottom and a fluidized layer at the top. You made the point at one stage. When you are in the convective things. I mean, the thing which is important is...
There is no up or down, because it's always rotating. So up and the top and the bottom side are the same.
That's true, but it's important that the roll do not affect the top and the bottom. I mean, it's as if your roll were squeezed between 2 boundary conditions, which, unless you start varying the height, are not. I mean, I'm not explaining myself properly. Then the question is that: is there a difference between the bottom layer? Sorry, is there a different configuration in the top layer when you have rolls and when you have got just shoot?
Oh yes, it's different. Because in the shoot flow regime, the whole granulate is fluidized. And in the convection regime, only the shallow layer.
That's.
Any more?